In this video, we will talk about what a multivariable function is. So before our class, before multivariable calculus, functions, when we looked at functions, our functions were of one variable. So what that meant, for example, was when we looked at our formulas for functions, so let me just write f for a function. When we input something into this, we're inputting, I write just one variable here. Okay, so let me just give an example of a formula. F of x equals x squared, for example. All right, so this was an example of a one variable function. And when we talk about functions, there are many ways to represent functions. So I want to talk about just what are some of the ways that we represent functions? What are their representations? So the first type of representation, actually I've written it down here already. It's this thing over here, which is a formula. So a formula is one way we can represent a function. So let me put a little bubble around that. Okay, we can also represent a function with a table. So with a table of inputs and outputs. So with a table, so where I keep track of the input, which in this case is x. I'm plugging in values for x. And my output is f of x. All right, so I'm just going to make a table of a few values. Let's input -1, 0, 1, and 2. So if we plug those in for x, when we square them, we'll get 1, 0, 1, and 4. So making a table like this might seem very simple and maybe not necessary for a function like f of x equals x squared, but for a more complicated looking function that perhaps where we don't know what the graph looks like, having a table of values can give us more concrete information about that function. Okay, so let's talk about another representation. Okay, so number 3, I'm going to do 2 more. So the third representation is what's called a mapping. We can think of a function as a mapping. Okay, so this one might be newer to us. Okay. All right, so with a mapping, I can think of all of the inputs as I'm just going to draw a circle to sort of visualize them. So in this case, I have these specific numbers I plugged into my table, like -1 and 0 and 1 and 2. And all of these inputs, they make up what's called the domain. And the domain for this function, at least the largest possible domain that I could have, is the real numbers. So I denote that with this R with another vertical line here. That's the symbol for the real numbers. So the domain in general means all possible inputs. Everything I'm allowed to input into my function. Okay, but then when we input these values, we get things out. So I'm going to depict them in a circle or an oval as well. Okay, so I'm just going to show some of the outputs that I get when I plug these inputs in. Okay, so in my table I had outputs like 0 and 1 and 4. Okay, so when I plug a -1 into my function, it gets mapped out to 1. So I can draw this line and draw an arrow to show, oh, when I plug a -1 in, it gets mapped to 1 as an output. Same thing when I plug 1 in. When I plug 1 in, it also gets mapped to 1 as an output. When I plug 0 in, that gets mapped to 0. And when I plug 2 in, that gets mapped to 4. All right, so the technical term for this circle of all possible outputs is the codomain. So the codomain is usually something that's given, or is something that we take away based on the context of the problem. So in this situation, I'm going to say that my codomain is all real numbers. All real numbers because no matter what I'm plugging in, the number that I'm getting out is a real number. So one thought that you might have had is, wait, don't we call the outputs the range? What is this codomain thing? So there is something called a range, and it's a little different from the codomain. It's a subtle point. So when we look at this function, the actual outputs we achieve are not all the real numbers. They're just a subset of the real numbers, and I'm going to sort of draw that in. So we're actually just getting a subset of the real numbers actually out of my function. So when I plug in this whole everything in the domain, it gets mapped to just this orange sort of subset of the reals that I'm drawing in here. So that orange subset is the range. And for this particular example, the range is actually just non-negative reals. And just in this example right here. So what's the difference? What's the difference between codomain and range in terms of definitions? So the codomain equals all possible outputs. So the possible outputs that I'm saying that I could have here are just real numbers. Those are the outputs that might be possible for me. But then range is all the achieved outputs. Let me put that in black. All of the achieved outputs. And that means the range is all of the outputs that we actually land on, that we actually get. So there might be some things in the codomain that we never actually land on. In this case, all of the negative numbers, we never actually land on the negatives, or there's nothing in the domain that gets mapped to the negative numbers. So you might be wondering, why am I telling you about codomain here? You know, we've been happy with our math knowledge up until this point with domain and range, and that's been good enough. So codomain is something that is emphasized more in classes like linear algebra, in fact, that's actually the class where I personally first learned about codomain. It's emphasized more in linear algebra and discrete math, and then definitely upper division math. But I'm introducing this term to you now, codomain, even though I won't personally stress it too much in our class, because I'm holding you to a high standard in our class. And I also want to show you that these things do exist. And this way, when you do take additional math classes beyond this one, you'll have been exposed to this term. So it isn't something that's completely new when you see it again in the future. Alrighty. Okay, so we have these so far three representations for functions. There is one more common one that I want to write down, and that is graphs. So we could represent a function graphically. So in this case, our function was f of x equals x squared. And it's really common with functions to let y, so assign a new variable to the output to f of x. And if we do that, we can write this equation as y equals x squared. So when we're doing this, if I start to draw my axes now, so the x-axis, so x, the variable x, is associated with my input. And the y-axis is now associated with the output. And we know what the graph of y equals x squared looks like. So y equals x squared is an upward facing parabola. We know that this vertex is at 0, 0. There's a point. Let me just draw a couple other points on this. So 1 at 1, 1. And then let's draw this point at negative 1, comma 1. All right, so that's the graph of this function. And let's write down the domain in the range now. So using the graph, well, the domain is all the possible inputs, or all the possible x values. And that's negative infinity to infinity. Or if I wanted to, I could just write it's all of the real numbers. And the range here, in interval notation, starts at 0, and I have a bracket, because I do achieve 0 as an output. And then I go onwards to infinity. And that's my range. So this was a review of one variable functions, how we've seen functions up until this point in our math classes. Now let's talk about multivariable functions. So in our class, multivariable calculus now, we will have multivariable functions. Multivariable functions. So multivariable just means more than one variable. We are going to be inputting more than one variable. So for an example, e.g., for example, I could have f of x comma y. So notice I'm having two inputs here. There's going to be an x and a y, two inputs. And let's just say my function is x squared plus y squared. So when I plug x and y into this, what x squared plus y squared ends up being is my output. So let's describe multivariable functions in terms of our different representations. So our first representation was a formula. So a formula, and this is a formula right here. Okay, so that is one of our representations. The next one was a table. So table. Okay, so for something like this, again, I'm going to have an input. Still going to have an input, but the input now is two numbers as opposed to one as it was for a one variable function. So this function is a two variable function because I'm inputting values for two variables. And I have an output still, and the output is just going to be one number. All right, so let's just do an example. If I were to input 3 for the x and -2 for the y, notice I can write my input as a point here, or as an ordered pair. The output is going to be 3 squared plus -2 squared, so 3 squared plus -2 squared, which is 13. That's my output. Just like with functions, I can also input things with variables. So if I were to input a for the x and b plus c for the y value, when I plug those inputs in, I end up getting a squared plus b plus c squared. And that's how I would write that output. All right, so I just scooted that over to give myself a little bit more room to write our next representation, which was mapping. So we can think of a function as a mapping that takes the inputs, the values in the domain, and maps them to outputs. So in this case, if I have a circle that represents my inputs, so I can have inputs like 3, -2, and let me do two others. Let me do 2, 0, and let me do 0, -2. So this first circle is going to represent my domain. The way I write a domain that consists of ordered pairs is I write R2. So it has this exponent type notation, but I don't say R squared. I pronounce this, or the way I say it is R2. So R2, and it represents the set of all ordered pairs x comma y, where the x and the y are both reals. Okay, so the 2 refers to, well, there's two numbers in it, and then the R means, oh, each of the numbers is a real number. All right, and the outputs here, the outputs are just reals, so I'll write R to denote those are the outputs. Okay, so this R stands for my codomain, not necessarily the range. Okay, so when I plug 3, -2 in, I get out 13. So that gets mapped to 13. I'll draw an arrow to indicate the direction. So 3, -2 is the input. That gets mapped to the output 13. And both 2, 0 and 0, -2, they will get mapped to 4. They will both get mapped to the output 4. So now if we think about this function, when we plug in an x and when we plug in a value for y, x squared plus y squared, the actual outputs that we achieve. So the actual range, remember range is all of the outputs that are achieved. Well, because of these squareds, I'm never going to get a negative value for x squared or for y squared. So my range should just be 0 to infinity. I can't get negative outputs. So I can represent that with my graph. When I take everything in the domain will just get mapped to a subset of the codomain, as it did in my previous example. So I'll indicate that with this orange region, and that orange region is my range right there. So the range here is this subset of the codomain. So as you'll see in possibly future courses in linear algebra or discrete math, when you see codomain again, there are some functions where the range is the whole codomain, but there are some functions where the range is not the whole codomain. It'll be a proper subset of it. And that's what happened in these two examples. All right. So we have one more representation. Which is graphs. Okay, so let's talk about graphing this function. Okay, so to graph this function, kind of like what we did with one variable functions, I'm going to assign a new variable. In this case, I'll pick z, to be equal to f of x comma y. Z will represent my output. So if we do that, we can write our equation as z equals x squared plus y squared. Okay, but we know what the graph of this looks like. We've graphed this back in chapter 12. So, if I draw my axes, I got a z-axis, an x-axis, and a y-axis. And if I draw the negative directions, a negative z, negative x, and negative y, this graph we've seen before. This is a paraboloid, an upward-facing paraboloid. In fact, the vertex of it is at the origin, 0, 0, 0. And then it faces upwards. So I'll draw one cross section of this. Comes around. Okay, but the paraboloid is like this. It's sort of curving like this. And that's the graph. This is, the precise term was, this is an elliptical paraboloid. So this is one of the reasons why we looked at the graphs, why we looked at 3D graphs back in chapter 12. So we'd be ready for chapter 14 now when we're talking about multivariable functions, because we're going to start multivariable functions by looking at functions of two variables like this. And when we have two variables, an x and a y, we need a new variable for the output, which I'm calling z. And then that's when we get a graph in 3D space like this. Okay, but eventually we'll also look at examples of functions of more than two variables, and then we'll get stuff in higher dimensions. Okay, so I want to just summarize a little bit. So when we talk about functions, functions can have a different number of variables that they're written in terms of. So when we have one variable, a function of one variable, so for example, like f of x equals x squared, the graph is two-dimensional, because you'll have x representing your input, and we assign a new variable to the output, so y. So now, as we did here with this example, f of x comma y equals x squared plus y squared, when we have two variables in our function, so our example was f of x comma y equals x squared plus y squared, the dimension of our graph will be three-dimensional, because we'll have inputs x and y, and we assign a new variable z to the output. Okay, so if we keep going like this, if we had three variables in our function, in fact, let me just say 3 plus, the dimension of the graph is going to be 4 or higher. Basically, however many variables I have in my function that I'm inputting into my function, the dimension of the graph is always one more, because I assign a new variable to the output. But as soon as I get to 4 dimensions or higher, we can't graph these. So they're harder to visualize, because I literally can't graph them. But there are workarounds, and we'll see some of those. So with a two-variable function, we can describe it using what are called level curves. And we'll see level curves and what they are in the next video. And with a three-variable function, we can describe it using level surfaces. And we'll see that a few videos from now, later in this section. So in terms of our goals for this section, we have now introduced what multivariable functions are and talked about representing them in these 4 common ways, as formulas, tables, mappings, and graphs. In the next video, we'll talk about what level curves are and how they help us visualize functions of two variables.